Welcome to the Professor's DuBois channel. This is Professor Corey, and this is a mini lecture that covers material from Chapter 12. Now, in our lecture, we only covered a small part of Chapter 12, and this is the portion of that shows phase diagrams. And these phase diagrams are going to show the relationship between pressure and temperature along with the state of the material. So let's take a look at one. This is an example of a phase diagram, and the colors kind of illustrate the different phases. So notice on the y-axis here we have pressure, and on the x-axis we have temperature. So we have the gas phase in this area that's colored, looks kind of pink or purple color. Our liquid is blue, and our solid is the yellow color. And oftentimes they don't indicate which area is the solid, the liquid, or the gas. So you'll need to come up with a method so you can, figure this out. Now the liquid's always in the center. That might help you. And another thing we can do is just go to really cold temperature and high pressure and just imagine what that would do to molecules if we got them really, really cold and slowed them down and then put them under a lot of pressure. Well, that would be a solid phase. So lower pressure, if we weren't pressurizing stuff, might favor a gas phase. So whatever works for you, you'll want to know those things. So some things we have going on here is we have equilibrium lines. So this line here is representing the equilibrium between solid and liquid. So on the line, both phases are present. Over here, we've got the liquid-gas equilibrium. And down here, we have the solid-gas equilibrium. And remember, going from solid to gas is what we call sublimation. And going the other direction would be deposition. So this is a good time to kind of brush up on those phase change vocab words because they're going to come into play here. Now remember I talked about the normal pressure? I usually try to find that whenever I see a phase diagram, and this one didn't have one, so I just wrote one in. So I said 1 atmosphere, and I put it up here. So for this example, this is my normal pressure. So this is my melting point or my freezing point, depending on which way I'm going. I could just drop an arrow down and read the temperature, and this would be my boiling point here. So that's basically the components of a phase diagram. And there's a lot of other stuff going on. So let's just dig into this a little bit deeper. This is a phase diagram for CO2. So again, right away, I try to find the normal pressure. And in this case, the pressure's in atmospheres. So normal pressure in atmospheres is 1 atmosphere. And you can see that's way down low on the scale. So at 1 atmosphere, this material, that's CO2, goes from solid directly to gas. It doesn't go through a liquid state. So that's called sublimation. And indeed, CO2 it does undergo sublimation. You may have seen this material. They call it dry ice. And just something worth mentioning is it's very, very cold. So CO2 in the solid state at normal pressure, what we'd experience in the lab, might be, minus 80 degrees Celsius. It's very, very cold. You don't want to touch this with your bare hands. So just something to keep in mind if you get a package delivered and it comes on dry ice, just be careful with that. Also notice that we've got this funny broken scale up here, and it just went non-linear. See, we went up to 73 here. They put this dotted line in it at a pressure of 73 atmospheres. So they put this little jog in there. You might see that. What else do I want to say here? Oh, we've got a spot here called the triple point. That's right here. And the triple point is where all 3 phases will exist in equilibrium. And you might not think it's that special because you might think, well, I could take a glass of water and throw some ice cubes in it, and I'd have vapor above the glass of water, and I'd have liquid and solid. But realize if we held this pressure, 5.19 atmosphere, in this temperature, negative 56.6 degrees C, then we would have those 3 phases. We could the ice wouldn't melt or the solid wouldn't melt. It would stay in three separate phases. And that's pretty cool. There's also a thing called a critical point, and that's up here. And I'm going to talk a little bit more about that in a different slide. But first, I want to talk about density. So moving on to the next one, we've got kind of a particle diagram, and we've got the gas phase on the right. And if we increase the pressure, we're putting these particles closer together, and we could say that the density increases. And this happens most of the time, but there is an instance where it does not, and that's with water. So water is actually more dense in the liquid phase, and this comes down to hydrogen bonding. If you look at the water molecules of the solid to the far left, notice the super neat arrangement in those dotted lines representing the hydrogen bonds holding these in place. And there's a lot of empty space in between the molecules. The water, on the other hand, we've got these intermolecular forces, the hydrogen bonding. They're being broke and reformed as the molecules move around one another. And there really are no intermolecular forces acting on a gas. So the evidence that liquid water is more dense, we can see this evidence just from watching what ice does. Ice, solid water, will float on liquid water, and that's pretty unique to water. And this is just another look at it, and it kind of shows on the right like a little bit of a three-dimensional solid state with, you could see all that empty space in there, and making it less dense. So if I look at this on a phase diagram, and let's just say I took a point where I'm in the solid phase and I increase the pressure. So take a look at this. I'm not going to change the temperature. I'm just going to increase pressure. Now, see what's happening? I enter into the liquid phase. So increasing the pressure is breaking those hydrogen bonds, and we're in the liquid state. So our liquid state is actually more dense than the solid state. And just something that's kind of neat is ice skaters, all of their mass is on a skate that's sharpened, really sharp, and it's a very small area on the ice. So there's a lot of force underneath that blade that's compressing that solid ice and breaking those hydrogen bonds. And the skates are actually sliding along on a thin sheet of water, which is really neat. So again, I can't emphasize the normal enough. We're in millimeters mercury here, so our normal is 760. Notice the dotted line up there. So our normal freezing point is where the solid and liquid interface is, and we can drop down and see the temperature. This is 0 degrees C, and the normal boiling point is 100 degrees C. And you should know that those are the freezing point and boiling point for water. You should know that. And what else should we know here? We've got the triple point. That's always good. Look at the slope of this line. That solid liquid interface. It's kind of like a rearward facing slope, and that's something that's unique to water, and that allows to increase pressure and go from solid to liquid. And most of the slopes, or anything but water, is going to have a forward facing slope. So let's take a look at one. So here's CO2, and you can see this slope is forward facing. So we can't start in the solid for CO2 and increase pressure and go into the liquid state. It's most dense in the solid state. So let's go up to this critical point. We've got this critical point where we start to enter into this region called the supercritical fluid. Now, the supercritical fluid is actually it's like a new phase. It's not a liquid or a gas, but it has properties of both. So let's take a look at this slide. We've got an image of an apparatus up in the upper right, where we're taking CO2, and if we look through like the side of this vessel and see what's going on in there, this might be what we see. So I've got the gas phase and the liquid phase here, and as we increase the pressure and the temperature, we start to lose that distinction between the two phases. And when we hit the critical temperature and pressure, we have this homogeneous phase that they call the supercritical CO2. Remember, this has properties of a liquid and a gas. And if we drew a Lewis structure for CO2, we'd see it's nonpolar. And if we use our like dissolves like, we can say, geez, we might be able to dissolve nonpolar substances in this CO2. And in fact, they do. And it's really neat because if I go back and we look at the critical temperature, it's 31 degrees C. It's not even that hot. So what that means is we can take something like plant material and grind it up and put it in this apparatus and get to this supercritical state, and it's not too hot to like decompose the plant material or burn it up. And so we need some high pressure there, and then we can simply separate our supercritical CO2 from that solid plant material, and then we can evacuate the CO2 gas phase, just release the pressure that goes back into the gas phase, and we're left with the oils that were extracted from that plant material. Really neat. That's really neat chemistry that's going on right now with things like essential oils and CBD. You've seen so much of this for sale everywhere. So supercritical CO2, this is a great solvent for extracting nonpolar substances. The alternate solvents they're using are like butane, and these are flammable. They smell bad. They're toxic. If there's residual material, this could be bad. So CO2 would be the way to go. All right, really quickly right now, I just wanted to go through a problem that was on some of your homework. And we've got our phase diagram, and we've got a mass of liquid krypton. They're telling us that this is krypton, and it's heated at constant pressure of 1 atmosphere from a temp of 119.8. That's right here. I'm at 1 atmosphere pressure, 119.8 to 170.4. And they want to know how much energy is required. They gave us some values. We've got an enthalpy of fusion, vaporization, the specific heat. And really what this comes back to is it's kind of like these heating curves that we did back in Chem 111. So this heating curve doesn't go with this. I just wanted you to see a heating curve. But where we are right here, when we're in the liquid state and we're on that equilibrium line, that's like being right here. So to calculate this, we have to calculate this part. That's the phase change going from liquid to gas. So that's going to be Q equals mass times the delta H of vaporization. And then we also have to do Q equals mass times MC delta T in the gas phase. So we have the specific heat of the gas. We have the delta H vaporization. We don't need the delta H of fusion. So you're going to do 2 calculations here, and you should try this on your own. I did it quickly, and I went to 3 sig figs and got 1690 joules is the answer I got. And you should be able to do that. It's going to be 2 calculations. First, you're going to calculate the amount of energy for the phase change, and that's going to be Q equals mass times the delta H of vaporization. Then you will use Q equals MC delta T to find the amount of energy it took to raise the temperature of the gas from 119.8 to 170.4. So give this a try. It's a good question, and hopefully you found this helpful. If you like the videos, give me a thumbs up. That would give me a little motivation to keep making these things. Please give me the feedback, and look forward to more videos from the Professor's Du Bois channel.